In this video, we're going to talk about how the matrix exponential works in the case when you have repeated eigenvalues. And I'm only going to focus on the 2 by 2 case. So again, we're trying to solve x prime equals ax, where A is a matrix with real entries. And we know that if A is diagonalizable, then we can easily solve the system. But in general, a matrix doesn't have to be diagonalizable. So in general, A isn't diagonalizable. In some sense, most of the time, A is diagonalizable, either over the real numbers or over the complex numbers. But if it isn't, it can be put into what is called Jordan form. In other words, we can write it as Pj P inverse, where J is a matrix in what's called Jordan form. The Jordan form is easy to describe in the case of a 2 by 2 matrix, and that's the only thing I'm going to describe. But there's a general theory of Jordan form for n by n matrices. So if A is 2 by 2, with a repeated eigenvalue lambda, and let's say that A is not the diagonal matrix with diagonal entries lambda, and A is not a diagonal matrix, then A will have to form P times this diagonal matrix, not diagonal matrix, but it's like almost a diagonal matrix, except with the 1 on the top right times P inverse for some invertible matrix P. Okay, let's talk about how you find P. So if you take this for granted, A equals P times this matrix, let's call this matrix J, times P inverse, one way to rewrite that, if you multiply both sides by P on the right, is that A times P is equal to P times J. So suppose that P has columns V1 and V2. So I can write it like this. Okay, well, remember that when you have a matrix times another matrix, so A times this matrix whose columns are V1 and V2, you multiply column by column. So the first column is A times V1, and the second column is A times V2. Then for the part on the right, you can think of this as taking linear combinations of the columns of the first matrix. So this matrix product here is going to be the matrix where the first column is lambda. So I go down this first column and I take linear combinations, right? So I take lambda times that plus 0 times that. So I'm going to get lambda v1 plus 0 v2. That's lambda v1. That's the first column. And for the second column, I take 1 of the first column plus lambda of the second column. So that's going to give me v1 plus lambda v2. So these two matrices are the same. That means their columns are the same. So if I set the columns equal, I get A v1 equals lambda v1, A v2 equals v1 plus lambda v2. I actually have a video in the Jordan form where I basically just go over the same thing. So I have this system of equations. So if I can find v1 and v2 that satisfy these two equations, that's going to give me my matrix P. So that's how you find the matrix P in the Jordan form. Okay, lambda is just the eigenvalue. Did I write that down? Yeah, lambda is the repeated eigenvalue. So let's rewrite this system of equations. I can subtract lambda v1 on the left for the first equation and get a minus lambda I. v1 is the 0 vector. And then if I subtract lambda v2 for the second equation, I get a minus lambda I times v2 equals v1. So first, you should find v1 that's in the null space of a minus lambda I. So in other words, you're looking for an eigenvector, right? And you want v1 and v2 to be non-zero vectors because p is invertible. So v1 is some vector, non-zero vector in the null space of a minus lambda I. Well, that's just an eigenvector, right, with eigenvalue lambda. And then once you find an eigenvector with eigenvalue lambda, then you have to solve for v2. So once you find v1 and v2 satisfying those equations, you can find what p is. And so remember that to solve x prime equals ax, we know that it's e to the at. So we need e to the at, and we know that that's equal to p e to the jt p inverse. So you just need to know what p is, but we know what p is, and now we just need to find e to the jt. So the question is, what is e to the jt? That's what we're going to do in the rest of this video, is to do the calculation. So this matrix J, let me just remind you, is this 2 by 2 matrix like this. And the trick is to write this as this matrix, the diagonal matrix with lambdas on the diagonal, and this matrix. So this is D, and let's call that D, and let's call that N. I think I did this in the previous video. But let's just do it again. The point is that D and N commute when you multiply, so e to the jt equals e to the dt times e to the nt. So that's e to the lambda t, 0, 0, e to the lambda t times, and then in the previous video I calculated e to the nt, and you get this, 1t, 0, 1. So if you multiply them, you get e to the lambda t, t e to the lambda t, 0, and e to the lambda t. So that's e to the jt. And that's how you solve a matrix system of differential equations when you have a repeated eigenvalue. So now I'm going to do an example, and this is an example that you probably have solved in a first course in differential equations. So solve y double prime plus 4y prime plus 4y equals 0. It's this initial value problem. Y of 0 is 1, y prime of 0 equals 3. Okay. So the first step to convert this to the matrix exponential is to write down this system as a, this differential equation as a system of differential equations. So the way you do it is you define x1 to be y and x2 to be y prime. And then since x2 is the derivative of y, that just tells you that x1 prime is x2. And then the point is that you take this differential equation and your x1 is y, and then your x2 is y prime, and then the second derivative is the derivative of y prime, so that's x2 prime. That's the idea. So then you write x2 prime by itself, you move the terms over, you get minus 4x1 minus 4x2. So then your matrix equation is x1 prime, x2 prime equals 0, 1, negative 4, negative 4, x1, x2. That's my matrix A. And here the characteristic polynomial is lambda squared plus 4 lambda plus 4 equals 0. So this is the characteristic equation that you get when you use e to the rt, right? You get r squared plus 4r plus 4. And this factors as lambda plus 2 squared equals 0, so then lambda is negative 2. So you get one eigenvalue, it's a repeated eigenvalue. So a plus I mean, I guess to check that this is, let's see. Yeah, the geometric multiplicity has to be 1, right? Because A is not a diagonal matrix. So A is not diagonalizable. So now we have to find V1 and V2. So we have to solve, where is it? This system, right? This system here. So lambda is negative 2. That gives us A plus 2i times V1 equals 0. A plus 2i times V2 equals V1. Well, A plus 2i is going to be this matrix like this. So to find an eigenvector, we just need to find a solution, a vector in the null space, so we can just swap the 2 and the 1, so you get 1 and 2, and stick in the minus sign, right? So this matrix times V1 will give you the 0 vector, and then to find V2, we have to solve A plus 2i, so that's this matrix, times V2 equals V1. So we set up the augmented matrix. We have to solve the system. We just need one solution. So we can take V2. I see that the second column is equal to V1. So I can just take 0, 1, right? I just take 0 of the first column plus 1 of the second column. So now I have a matrix P. It's the matrix whose columns are V1 and V2. So that's P. My matrix J is this matrix. So P inverse, I can use the formula. Fortunately, it's easy because the determinant is just 1. And now I just swap the A and D. Well, A and D are the same. So I just get 1s in the diagonal. And then I replace B and C by negative B and negative C. So I get this. So that's P inverse. And E to JT is just, we calculated this. In general, it's going to be this. Okay, so we calculated the general E to the JT, and in this particular case, when your lambda is negative 2, this is what you get. So now we're ready to put everything together, because the solution is y of t, y prime of t, right? That's x1, x2, equals p times e to the jt, just this, times p inverse. So this matrix, what I have here is e to the at, and now I have to multiply by the vector that gives you the initial values. So it's going to be 1, 3. And what are we going to get? Well, if you multiply, see, what's nice is that you're only solving for y of t, right? Because the question is, what's y of t? So you only need the first component. So if I take these two matrices and multiply them, I get e to the negative 2t, t e to the negative 2t, and then I'm going to get something, and I don't even care what that thing is. Then when I multiply these two matrices together, I get 1, 5. So now I can multiply them and find what y of t is. Remember, I just need the first component. So I just multiply, I get e to the minus 2t plus 5t e to the minus 2t. So That's the solution. Notice the t, right? So when you first learned how to solve this second order differential equation with the repeated eigenvalue, or repeated root, as they say, you learned that there has to be a t in the second solution. And you can check that if you have a t, it works, but now you see where the t comes from the matrix exponential. It comes from this t here that shows up in the matrix exponential because the Jordan form has this t here on the top right. Okay, and that t corresponded to the 1 in the Jordan form matrix. So that explains how all of these concepts kind of tie into each other, right? So the t can be explained using the matrix exponential in the Jordan form.